Hello everyone, today I'm going to explain the activation energy. That is one of the parameters that we discussed before in Arrhenius equation. And why this is actually important? Because it's important for either chemical or biochemical reactions. And the activation energy is the energy needed for reactant to colloids and to rearrange it again to form the bond for creating the product from these reactions. In a simple form, it's a minimum energy that is needed for a reaction to occur. So, for example, here, and we discussed before, basically, we discuss why the temperature is an important factor for reaction rate. And for example, if we have a reaction rate at temperature 2, Kr2, and we have reaction rate Kr1 at temperature 1, so the natural logarithm of this value equal to the activation energy divided by the R, which is the universal constant of gases, and multiply by 1 over T1, and the T1 here is the temperature in Kelvin, and minus 1 over T2, which is also a temperature in Kelvin. So a high energy or activation energy indicates that the rate is strongly dependent on the temperature. However, if we have EA0 or activation energy 0, this means that the rate is not dependent of temperature. Can be negative, it might, but this is very rare, means that the activation energy decreases, or activation energy negative means that the rate of reaction decreases with temperature, which is very rare case. Okay, so now what does it mean activation energy? If we look at these two figures again, 1A on the left and 1B on the right, and here this is the potential energy for reactant and for products on y-axis, and the x-axis is the reaction coordinate, which is maybe you can consider it as a time for reaction, and the same actually also for B. And here, for example, if we look at this one, if we have a potential energy for reactant A and B is at this point, and the reaction and the potential energy for product at this point, means that the activation energy here is the distance between the potential energy for AB over the activation complex here, activated complex, and then proceed to products. In this case, if we have activation energy larger than 0, and in this case also the change in the overall change in the potential energy, which is dE less than 0, and this means that the product have lower, of course. If we look at this figure, we have the product have lower potential energy, and in this case, the overall change in the potential energy is negative, means that the reaction is releasing energy, or exothermal reaction. On the other hand, if we have here the products, and here, if we have the reactant and we have the products, in this case, the activation energy is larger or higher, and in this case, the overall or the change or the overall change in the potential energy is more than 0. And in this case also, we can say that the product have higher potential energy than the reactant, and in this case, we have to put energy to proceed through this reaction, or to make this reaction to occur, means that this is actually endothermal reaction. Again, this is the concept basically for the activation energy is the concept of catalysts, and catalysis is the process of adding catalyst to facilitate reaction. These catalysts can be either biological, like enzymes, or maybe chemical catalysts. Any catalyst that you add for reaction to proceed faster, to be more efficient, which means that catalyst is the factor that make or the lower lower or reduce the activation energy. So in this case, for example, here you actually here the reaction progress over time, and if you have the energy, if we have two reactions, one uncatalyzed and one catalyzed reaction. So if you look at this difference between you have, of course, this transition state means that the complex between the reactants, and here this is the activation energy in the presence of catalyst, and here's the activation energy in the absence of catalyst. So in this case, you would actually expect that more energy to be needed to have this reaction to occur. But if you add the catalyst, this smaller amount of energy or activation energy needed for this reaction to occur. So in this case, the EA is less than EA1 is less than EA2, means that the activation energy needed in this case is less in the presence of catalyst. Means that you have to have a faster reaction in the presence of catalyst. Again, this can be enzymes or can be chemical reactions. So for example, actually here, this is just a very quick example for the activation energy. If you have a certain biological reaction and have activation energy of 50 kilojoule per mole, and how much faster will be this reaction at a temperature of 37 degrees C against 25 degrees C. And if we have the R is 0.8, is 8.314 joule per mole per Kelvin. Again, we can use the relationship between two reaction rates. And as we mentioned before, is the natural logarithm of KR2 over KR1 is AA divided by R times 1 over the temperature of reaction of T2 in Kelvin minus 1 over reaction of 1, the reaction temperature of at the temperature, the first temperature, and we can get actually this kind of value here, 7.81. What does it mean? It means that the reaction rate in the case 2 equal to equal to 2.18 KR1, which means that at higher temperature, this KR2, this is the reaction rate at 37 degrees C, is almost double of the reaction rate at temperature 25. As a rule of thumb, you may actually heard this before, that the reaction is doubling in speed, or reaction rate is doubling for every 10 degrees C. But this, of course, dependent on the activation energy, but you can actually just approximate it by say every 10 degrees C, you can actually expect the rate of reaction is doubling. I hope this is actually helpful, and if you have any question, let me know. And I hope this is useful for you. See you next time.